Welcome to Unstuck. Today the most famous bug in smart contracts, reentrancy. A vault paid people out before it updated its books, so an attacker could ask for their money again and again in a single transaction and empty the whole pool. We'll see the one line that did it, run the attack ourselves by hand in Remix, prove it with the Foundry tests, watch it on a real block explorer, and fix it by moving a single line. Here's the heart of it, no? A vault's withdraw function. It reads your balance, sends you the money, and then sets your balance to 0. Read it in that order, because the order is the entire buck. It sends first and updates last. First, what a vault is. You deposit it and it credits your balance. You withdraw and it sends that balance back and marks you as paid. Many people deposit into the same pool, so the vault holds far more than any single person's balance. Remember that. There's a big shared pot and each person is only supposed to take their slice. Here's the whole attack as a flow, and this is the part that trips everyone up. So follow the numbers. 1, you click steal just once. 2, steal calls the vault's withdraw. 3, the vault sends you 1 ether, and here's the key. Sending ether to a contract automatically runs its receive function. 4, inside that receive we call withdraw again. That's the re-entry, and the vault hasn't zeroed our balance yet, so it still thinks we're owed money. 5, it pays again. 6, receive fires again. And withdraws again. Only at the very end, step 7, does the vault finally set our balance to 0, but by then the pool is already empty. So steal was a single click, it's received that, did all the rest. Back to the code, the vulnerable order highlighted. The call that sends the eth comes first, marked interaction first. The line that zeroes the balance comes last, marked effect last, too late. Between those two lines, the attacker's contract re-enters withdraw, and the balance still hasn't changed. That gap is the whole vulnerability. And here's the fix, the same function with one highlighted line moved. Set the balance to 0 first, effect first, and only then send the eth. It's called checks, effects, interactions. Why does moving one line fix it? Because now when the attacker re-enters withdraw, the balance is already 0. So the require fails and the whole thing reverts. Let's watch the attack happen, then prove the fix stops it. Let's do this attack by hand in Remix, so you see every single click. On the right is our vulnerable vault and the attacker contract that will drain it. We started by deploying the attacker and we send it 3 ether. Its constructor creates the vault and seeds it with those 3 ether, standing in for other people's deposits already sitting in the pool. How much is in the vault? We click pool balance, it reads the vault's balance and returns 3 ether of other users' money waiting there. Now we join looking like a completely normal user. We click attacker deposit and send just 1 ether of our own into the vault. Check the pool again. Pool balance now reads 4, their 3 plus our 1. So far nothing looks suspicious at all. Here's the theft, and it's exactly the diagram we just walked through. We click steal one time, it calls the vault's withdraw, which sends our 1 ether back, but receiving that ether runs our receive function, which immediately calls withdraw again before the vault has set our balance to 0. So 1 click from us and the receive function does all the looping. So the vault pays us again and again, looping until it's empty. Watch pool balance now and it's 0. The entire pool gone from that 1 click. So what did we walk away with? We click my loot and it reads 4 ether. We deposited a single ether and we left with 4. We just took the other user's 3 by asking for our money before the vault could mark us paid. We did all that by hand. Now let's prove it with a test and read it line by line. It deploys the attacker with 3 ether, then asserts the pool holds 3. Then the attacker deposits 1 ether and it asserts the pool is now 4. Then it calls steal and asserts 2 things. The pool ends at 0 and the attacker's loot is 4. Every manual step we just did, now pinned down by code, And there's the run. Pool after the seed 3, after our 1 ether deposit 4, after steal 0, attacker loot 4. It passes, which means every assertion held, so the drain is real, exact, and repeatable. Now the fix. The same test, but against the fixed vault. It deposits 1 ether, then wraps the steal call in expect revert. It demands that the attack fail. And afterwards it asserts the pool never moved. Still 4, in other words, it proves the attack simply cannot run anymore. It passes. The re-entrant withdraw reverted exactly as expected, and the pool stayed at 4. So the one-line fix moving the balance update up doesn't just look right, it provably blocks the exact attack that emptied the vault. And this is not just a local sandbox. We deployed the very same attacker and vault to the Sepolia network and verified them on Etherscan. Source code verified, exact match. Anyone can read the vulnerable withdraw for themselves. This is the steal as a real transaction. Etherscan decodes it as a call to steal and it succeeds. The reentrant withdrawal loop runs on a live chain and empties the pool. The drain, recorded permanently in a block, you can click through. Here is that same steal, but against the fixed vault of the same network. Status failed because the balance was zeroed first. The second withdrawal reverted on chain, exactly as our test predicted. A real decoded failed transaction and the fix proven in public. Side by side, the old vault sends first and updates last, so the attacker re-enters in the gap and drains the pool. The fixed vault updates first and sends last, so re-entry finds a zero balance and reverts, as the rule underneath is a mantra worth memorizing. Checks, then effects, then interactions. The takeaways. Always update your state before making an external call, checks, effects, interactions. Remember that any call that sends ETH can hand control back to the receiver, who can call you again. For extra safety, add a reentrancy guard, a simple lock that blocks a second entry. And whenever you see an external call, read the next lines asking, what happens if they reenter right here? Let's recap. The vault's withdraw function sent the ETH before it zeroed the balance. Sending that ETH ran the attacker's receive function, which re-entered withdraw, and since the balance was not updated yet, the vault paid again and again until the shared pool was empty. The fix is to zero the balance first, checks, effects, interactions. We saw it by hand in Remix in the Foundry tests and live on Etherscan. A quick note, if these breakdowns help you ship safer contracts, the wallet is on screen and there is a Ko-fi link in the description. Every tip funds the next reconstruction. Thank you. Your turn. Comment the hack you want me to reconstruct next and I'll build it live, just like this one. If it helped, hit like and subscribe so you catch the next one. This was a genericized reconstruction, the lesson, not the names. Thanks for watching and I'll see you in the next one.